hand if you've ever seen an object levitate or float mid-air. Okay, quite a lot of you. Well, the first time I ever saw this was about 10 years ago when I was a young girl in middle school. And I remember walking into a lecture room. It was smaller than this. And there was a guy at the front giving a presentation on computers of the future. And he was talking about futuristic new ideas for computers. And one of them was quantum computers. And then he explains a bit about it, and then he showed us an experiment live in person. And I want to show you a video of the experiment. It was of an object called a superconductor levitating.
Liquid nitrogen. One of the most amazing things about superconducting levitation is what you see here. Not only does the disk hover above the track, but it can hover below it as well. In fact, we can shape the track any way we want, and the disk zooms along at exactly the same height, no matter its orientation, with no friction or resistance.
So I was amazed when I saw this experiment live in person. And I don't have a superconductor here with me, but I do have this levitating magnet here, as you can see on the stage. And to prove to you that it is actually levitating, I can put this underneath it. And one of the cool things you can do is put objects on top of it, for example, this donut. So now, oops. We have a spinning donut. And later in this talk, you'll understand why I'm using a donut. So, after I saw this talk on computers of the future, I was really amazed. And one of the reasons that the superconductor can levitate is because of quantum physics. And quantum physics basically describes how the world works at the most fundamental level, the level of atoms and subatomic particles, such as electrons. And a quantum computer is a new species of computers that uses the strange and amazing behavior of quantum physics in order to solve some computational problems significantly faster. And a quantum computer now, it's no longer a computer of the future. It's actually the computer of today, because quantum computers do exist, and we're in a really exciting time in history where anyone in the world can actually program a quantum computer. All you need to have is internet access. And I will demonstrate that later in this talk today. So after I saw this talk on computers of the future 10 years ago, I was inspired to study physics and computer science. And the talk was in Reading, England, which is my hometown. And shout out to Vincent, who also lived in Reading. He's one of the organizers of this, and it's rare to find people who have lived in Reading in England. But after that, I ended up going to MIT and Harvard to study physics and computer science for my bachelor's, and then started my Ph.D. at Stanford University, where I'm currently at doing research in quantum computing. And recently, I've been at NASA through KBR in their Quantum Artificial Intelligence Lab. Now, one of the research questions I'm interested in is, what is the potential of quantum computers? What could we do with a quantum computer that is practically impossible to do with our current computers? And in fact, we're going to talk about the 3 Ps of quantum computing in this talk today. The first one, as I just mentioned, is the potential. The second one is programming. How do you actually program a quantum computer? And lastly, we're going to look at the progress. How much progress have we made, and what is left to be done in this field? So to start off with potential, let's look at some examples. And I have 3 categories of applications. The first one is factoring/search. So let's take a look at an example. Let's say I give your computer the number 15, and I say, now find me 2 prime numbers you must multiply to give 15. Well, of course, that's extremely easy. Your computer knows 5 and 3 multiply to give 15. But what happens if I give it this 617-digit number? And now I say, multiply two numbers. Well, your computer isn't going to be able to handle that. In fact, it's estimated it could take up to 1 billion years using the best known algorithms just to find out what those two numbers are. And when I say current computer, I want to clarify that I'm referring to a classical computer. And this is basically any computer that's not a quantum computer, so your laptops or your phone. So on a classical computer, it would take up to 1 billion years just to find what those two numbers are. But what about a quantum computer? How long do you think it could take? And I actually have a poll. I want to see what you guys think. So you can go to polev.com/quantum225 and enter in your response for how long you think it could take on a quantum computer to find those two numbers to factor a 617-digit number. So I'll give you guys a few seconds. Okay, let's see what you think. Okay, so you guys know your stuff. That's great. So you're actually right. It's about 100 seconds on a quantum computer. So that's crazy, right? We're going from, yeah, the answer always increases once I tell the real answer for some reason. So on a classical computer, it would take up to 1 billion years, but on a quantum computer, it would just take 100 seconds. And this is an example of the potential of quantum computing. Now, how do we know this is possible, that if we had the ideal quantum computer, it would take this long? Well, that's because people come up with quantum algorithms. And a quantum algorithm is basically just a set of instructions that you give to a quantum computer, maybe assuming it's ideal or perfect. And so Peter Shor, who's a professor at MIT, created a quantum algorithm called Shor's algorithm, and he proved that it was so much faster on a quantum computer to find those two numbers. Now you may think, okay, is this an interesting problem? Well, it is, because if you're familiar with encryption, you know that those two numbers are essentially what's keeping all of your internet data secure. The fact that it could take 1 billion years on a classical computer means that your bank information, your credit card information is secure by encryption. But on a quantum computer, essentially you have the key. So you could break encryption methods. And this is actually one reason why quantum computing became popular, because people started to worry, oh wow, this could have implications on society. So should you be worried that the internet will break tomorrow and it will explode and everything will be bad? Well, no, because as you'll see later in the progress part of this talk, we actually haven't built a quantum computer that can find those two numbers of a 617-digit number. However, it is an important problem to think about, because people estimate it maybe could take 10 years just to replace and re-encrypt all of our data with a new encryption method that could be safe against quantum computers. So it's something we should start thinking about, because maybe in 10 years we'll have that quantum computer. And there's also this thing called store now, decrypt later, where people could basically store encrypted data now, and then maybe when we have that quantum computer, decrypt it. So it's important for us to start replacing the encryption systems as soon as possible. So another application of quantum computers is unstructured search. Now, to illustrate this, I have a bag with 100 balls. So as you can see, there is no structure to these balls. And let's say there is a number from 1 to 100, and each one's unique. Essentially, what a classical computer has to do, if I ask you to find, let's say, the ball number 3, it has to pick up a ball, check whether it's the number 3, and then continue until it finds the ball. So if you had 100, it could take up to 100 tries on a classical computer if there's no structure. But what about a quantum computer? Well, it could actually take just 8 tries, even when there's no structure. And again, this is using a quantum algorithm called Grover's search. And as you can see, we can generalize it. So you could say, let's say you have a database with n entries, you could find one particular entry in just up to square root of n tries on a quantum computer. And this is using a quantum algorithm called Grover's search. And later in this talk, we'll see actually how you can implement this algorithm on a quantum computer. So that's one category of applications. The next one is understanding nature. So we obviously know that everything around us is made up of atoms and molecules, and they all follow the laws of quantum physics. But it's quite hard to actually simulate and model how these molecules behave on our classical computers. So it makes sense. We want to use a quantum system, a quantum computer, to simulate and understand a quantum system, which essentially is all of nature. So what applications could that have? Well, we could potentially design new medicines and drugs, because that's basically made up of a bunch of molecules interacting with molecules in your body. So if we could simulate those drugs and medicines more accurately, we could potentially design more effective medicine. Or how about materials? People are trying to consistently come up with new types of materials that could be used for your laptop or your phone. And again, it's just made up of molecules. So if we could simulate that with a quantum computer, we could potentially design new types of materials with strong properties that we want. So that's another application. And lastly, of course, I can't be at a software conference without mentioning machine learning. So there is an application called quantum machine learning. And this may sound like a lot of buzzwords, and it kind of is, but it makes sense, because if you look at the underlying mathematics, machine learning is a bunch of linear algebra with matrices and vectors, and actually quantum computing, as you'll see a bit later on, is also a bunch of linear algebra with vectors and matrices. So the two nicely map together. So here are three potential applications of quantum computers. And as you can see, they're so broad that they could impact a whole variety of industries, from AI to medicine to space, logistics. And no wonder people are excited about it, and I think they should be, because with quantum computers, we could solve the unsolved problems. Things that are practically impossible to solve on our classical computers could be solved in just seconds on a quantum computer. So now you might be saying, okay, well, how does it do this, and how do you actually program a quantum computer, and how is it able to do this? Well, this is the programming part of the talk. So we're going to look at how do you actually program a quantum computer. And to understand this, we have to start at the basics. So there are three basics, you could say. The first is the quantum bit. So as you know, computers store and process information in bits, zeros and ones. Any character can be a sequence of bits. And to illustrate this next part of the talk, I have with me a donut. So let's say the classical bit, the 1 is the frosted side, and the 0 is the plain side. So this is our classical bit. Well, what about a quantum bit? Well, actually, a quantum bit, also known as a qubit, is actually the same, sort of. It can also be 1, and it can also be 0. Now, throughout this next part of the talk, I'm going to have a little section called A Deeper Understanding, so that you can gain more intuition behind what's going on if you're familiar with the mathematics. Now, if you've forgotten your linear algebra or you're not familiar, don't worry, you can actually understand all of this with just the donuts. That's the whole point of it. But the mathematics sometimes helps you understand. So in quantum computing, this qubit, we actually represent it as a vector. So this 0 is this vector, and this 1 is this vector. Okay, well, what's different about the qubit? Well, obviously, it has quantum physics, as in it can exhibit the quantum behavior. And so one quantum behavior is superposition. Now, I like to think of superposition like a spinning donut. When it's spinning, I ask you, is it 0 or 1? You say, well, it's both. It's a combination of 0 and 1, hence our levitating spinning donut. So it's 0 and 1. Now, the way you write this mathematically is literally you add the vectors together. So we have the 0 bit plus the 1 bit, and we have superposition. Now, you may think, oh, it's actually not that simple. There is some other constants, and this is for normalization's sakes, just to be technically correct, but don't worry about that. So as you can see, what is the power of superposition? Well, let's say I give you a donuts box, and you open up the box, and inside you see 2 donuts. Either you see 0, 0, either you see 0, 1, or you see 1, 0, or you see 1, 1. And this is essentially how a classical computer processes. It can only process one combination at a particular time. But if I give you a box now with 2 quantum bits, they're both spinning, and I ask you, what combination do you see? Well, you actually would say, I see all of the combinations. And this is what a quantum computer can do. It can actually process all of the combinations of bits at the same time, essentially. And so I have another poll for you. If you had 300 qubits in superposition, how many different combinations do you think there would be? I'll give you guys a few seconds. All right. Okay, interesting. You guys just went with the largest number. So the correct answer is actually 10 to the power of 90. So why is that? Of course, and then the answer increases. Okay, I'm going to stop that. So why is it 10 to the power of 90? Well, that's because when we have n qubits, it can be in 2 to the power of n combinations. So in this case, we had 300 qubits. That's 2 to the power of 300, which is roughly 10 to the power of 90. I couldn't make it that simple, just saying 2 to the power of 300. So that's why we had 10 to the power of 90. And that actually is an insane number. That's more than the number of atoms in the observable universe. So essentially, with n qubits, you can represent 2 to the power of n classical bits of information. And that's one of the powerful parts of superposition. Okay, so we've looked at the quantum bit, but how do you actually program this and manipulate the quantum bit? Well, we have to use something called quantum gates. And if you're familiar with our classical computers, they also have these logic gates. For example, if you have the bit 0, you put it through the NOT gate, it ends up being 1. And so then this is essentially how a computer is made, very simplified. You build modules and then chips and circuits out of that. So in quantum computing, it's actually very similar. We have things called quantum gates. So, for example, I have some gates with me here. Here is, I've got too many gates. Okay, here's one of the gates. It's called the X gate. So this is a quantum gate. And we also call it the bit flip gate. So you could probably think about what this does, but basically, if it's 0, it goes through the gate, and then it ends up flipping it to 1. And it could also be the other way. If it was 1, it would go through the gate and flip it to 0. And remember that this is all linear algebra. So essentially, a gate is a matrix in quantum computing. So this is our X gate. It's this matrix. And then we multiply it by the input, which is the vector, the 0. And then the result is the output. So in this end, we end up getting 1, which is the 1 bit. So that's not very interesting, right? Because we can do this classically. Well, of course, there are other gates. So now we have another gate called the Hadamard gate. Now this gate, you put it through, and then it ends up in superposition. It ends up spinning. And this is called the Hadamard gate. And this is one of the quantum gates. Now, think about it. What happens, do you think, if you put something that is spinning? Oh, okay. So actually, I want to go through the deeper understanding part again. So this is a matrix. As I mentioned, you multiply it by the input. So in this case, it's 0. And then when you go through, it ends up the output, the vector. So if you just multiply those matrices and vectors, you end up getting the superposition qubit. So now, my question is, what do you think happens if you put something that's spinning through the Hadamard gate? Okay, there's some chatter. Yeah, so it actually ends up being 0. So as you can see, obviously, the effect of the gate depends on the input. And again, if you look at the deeper understanding behind this, it's because it's just the matrices and vectors. So we're multiplying the same gate by the superposition qubit, and then we end up getting our 0 qubit in the end. So here is a quantum gate. Now, the whole point of a quantum algorithm is you can execute it using the quantum gates. So remember Grover's search? This was the one with the balls. So in this case, let's simplify it. Let's say we only have 4 balls, and we want to find the ball number 3. So how would you implement this on a quantum computer using the gates? Well, classically, it would take up to 4 tries because you have 4 balls. And in the quantum case, you could actually just find any ball in 1 try. So we have to convert the number to bits. So in this case, we're looking for 1, 1. And we build a quantum circuit. So essentially, a quantum circuit is just a sequence of quantum gates. So if I put these gates together, I can have a quantum circuit. And then, as I showed you, essentially the qubit is going through the gates. So you can see first it goes through a Hadamard gate, then it goes through another Hadamard gate, then it goes through an X gate, then an X gate, then a Hadamard gate. So this is 1 qubit. But because we're having 4 numbers, we actually need to add another qubit. So this qubit has other instructions. And then we have this other gate, which basically connects the 2 qubits together. So this is actually the quantum circuit for Grover's search, which is the unstructured search problem, in the case that you want to find the ball number 3 with 4 balls. So as you can see, it's actually, you know most of the gates now to actually implement this algorithm on a quantum computer. So here we have the quantum gates, but how would you actually program this? Well, this is the quantum programming part. So you can program a quantum computer using the quantum gates. So in this case, since we're at you're all familiar with Java, we have the strange quantum computing API for Java. So you can go to this GitHub link, and I'm going to briefly go through the explanation of this code. So essentially, we can create the quantum circuit, and then we start off with the simulator. Now, what do I mean by simulator? Well, remember that it's actually just a bunch of linear algebra. So you can simulate what a quantum computer would do on a classical computer by just multiplying the matrices. Now you might think, wait a second, then what's the point of the quantum computer if we can just do that? Well, remember the n and the 2 to the power of n bits is that basically as the number of qubits increase, the matrices get exponentially larger. So it practically becomes impossible to start multiplying these matrices and on a classical computer. So for, let's say 10 qubits, that's fine, you can simulate it, but for 100 qubits, you cannot. So that's why we have the simulator, but you could actually just run this on an actual quantum computer. And in this case, we create a program, and we're saying that we want 1 qubit in this program, and then we have the steps that we're going to add to this program. So in this case, we're going to add the Hadamard gate to it, which puts our qubit in superposition. And then this is all the syntax, we just add this step to the program, and then we run the program on the simulator, and it would give us the result of what a quantum computer would give us. So as you can see, you can actually code in Java what a quantum computer would do, and so in some cases, you can actually connect it to a real quantum computer, so actually run it on the real device. So you might be thinking, okay, that's great, but why is quantum computing more powerful than classical computing? Well, the whole point is that we want to use quantum effects such as superposition to solve problems in new ways, hopefully leading to better results. And to illustrate this, I have a little analogy. So let's say you go to a classical donut shop. Just go by. And in this classical donut shop, they want to play a game with you. So what is the game? Well, they say they have 2 boxes. So they have the yellow boxes. This is the baker. So they have these yellow boxes. And you have 1 box. And you have the red box, which I will get. So here is the red box. Now, the game is you have a donut. And it's going to go through all of these boxes. Now, the thing is, no one can see what's happening inside the boxes. You can only hit these buttons. So you have a couple of options. You have the option to, so here we have our donut, it's 0, and then it goes through the box. And then the baker is the yellow. So the baker has the option to flip it or to do nothing. Okay, and then it goes through the red box. You have the option to flip it or do nothing. It goes to the yellow box. You have the option to flip it or do nothing. and it comes out at the end. Now, if it comes out as 0, the baker wins. But if it comes out as 1, for whatever reason, when you're flipping it, then you win. So would you want to play this game? Maybe. You have basically a 50% chance of winning, right? It's kind of random. You're just flipping or not flipping. But what happens now if you go to a quantum donut shop? Now, at the quantum donut shop, the baker has access to a quantum computer, but you don't. So now that the baker has access to the quantum computer, they essentially have quantum boxes. So in this case, we have one of the, now it changes to this one. So now the question is, would you want to play this game? Raise your hand if you would want to play this game against the quantum computer. Okay, you guys are seeing what's coming. Yeah, so you're right. With the quantum computer, the baker can now win 100% of the time. So you'd have no chance of winning. Now, why is that? Well, as I said, the baker has these 2 new boxes. Now they have a new option to do the Hadamard, remember, which is the one that puts our qubit into superposition. So I have a question for you. Here are the boxes. What 2 buttons on this one and this one should the baker press in order to win 100% of the time when the donut goes in as 0? So let's see what you think. So when thinking about it, you can think about it in terms of the donuts, or you can think about it in terms of the mathematics if you were writing down the matrices and the vectors and want to multiply them. Let's see. Okay, interesting. Yeah, so you guys are correct that you won the Hadamard. And obviously you guys were like, yeah, there's no point of doing the flip. Yeah, so that's correct. You would put the Hadamard. So why is that? Because let's say it's 0, and we put it through the first gate. So this is all the box, and it now comes spinning. Now what happens if the red person, you, choose to do nothing? It's still spinning. And remember, when you put something spinning through the Hadamard gate, it ends up flipping to 0. Now, in the case that you choose to flip, so it's spinning, if you flip something that's spinning, it's still spinning, right? So it's still in superposition, regardless of whether you flip it or not. And so then we put it through the second Hadamard gate, it ends up as 0. So that's an example. And now you may think, oh, well, that's unfair because the quantum computer has an extra thing. But actually, that's the whole point, is that the quantum computer has these new gates, these new quantum effects that allows us to think, can we solve a problem in a new way to get a better result? And this may seem like a simple game or a trivial game, but actually, there's a whole paper on it. Oh, so I have a bunch of animations of it spinning, so then it comes out as 0. So there's actually a paper about this. It's called Quantum Strategies, and the paper is basically about this game. And interestingly enough, there's another paper that actually connects this quantum game to quantum algorithms. So remember we had Grover's search, which is the algorithm with the balls. So actually, in this paper, the author argues that this quantum game is structurally similar to how quantum algorithms work for their quantum strategies. So now you have a little bit of a taste for why quantum computing can be better. And the whole idea is we need to think of problems in new ways. So here we have the programming part of quantum computing. Now you may think, okay, well, how much progress have we actually made in this field? So now we're going to look at the progress part. And there are 3 main parts we're going to look at. The first one is the hardware, because as I said, all of this really depends on, can you actually run this on a real quantum computing device? So how do you build quantum computers? Well, first of all, the question is, how do you build classical computers? We know they're made up of transistors, which basically act as 0-1 by blocking or allowing the flow of electrons. But it didn't actually used to always be that way. People used to use vacuum tubes instead of transistors. But it ended up being that transistors were, more scalable, a lot easier to use, cheaper, so that's why we have them today, and they took off, as you know, with Moore's law. But I use this because actually there's different ways to build a quantum computer. So for example, one way is superconductors. And remember the superconducting levitation I showed you at the beginning? Part of the reason I showed you that is because superconductors is actually one of the main ways to build quantum computers, right? Because it's because of quantum physics that the superconductor has all these properties. Now, I should note that I did say this sometime, and then some people thought, oh, that a quantum computer is like a levitating computer, but that's not the case. So it's not actually levitating, but it just uses the superconductor as a substrate. So then we have trapped ions, which are basically atoms with a net electric charge confined in a particular space. We have photons, which is light. And then finally, we can even have diamonds to build quantum computers. I have a friend at Stanford who's working on diamond quantum computing, and he was like, casually, yeah, if you ever want some diamonds, just let me know. And I was like, yes! I should be working the hardware. So here are all of the different ways. Well, there's actually a lot more ways, but here are the main ways to build a quantum computer. And essentially, you want something that can be a quantum bit. It has to be 0 and 1, and also be in superposition and have the other quantum effects. And no one really knows what's the equivalent of the transistor quite yet. Actually, I would say superconductors is the most popular one that a lot of the big companies are using. But who knows, maybe a new technology will overtake it. So what is the challenge with building the quantum computer? Well, just like with the spinning donut, you can see eventually it will stop spinning. And it's actually the same with qubits. Eventually, it loses its superposition. And that makes it difficult because if it loses its superposition in a short amount of time, you can't have that many gates. You can't have too long of a computation. You have to make it short. So this is one of the biggest challenges with quantum computing. And you can imagine that if you had even more qubits, it's even harder to control all of them. But despite that, we have built quantum computers. So here's an example of the IBM quantum computer. And interestingly enough, all of this equipment that you see, this is basically to control the quantum chip. And the quantum chip itself is like this small at the very bottom of this like chandelier-looking thing. So as you can see, it's pretty exciting. We've actually built quantum computers. But to give you an idea, again, of how complicated it is, I recently went to a talk by Google AI Quantum, and they gave me permission to use the slides. But the whole point is that don't worry exactly what it is, but this is to basically control 2 qubits. This is the hardware process. And as you can see, there's a lot of different connections and a lot of different points. And 1 dot equals 1 physics experiment. And the guy who's giving this presentation, this was his Ph.D. So yeah, this is just to control 2 qubits. So as you can see, it's very complicated. But that's why it's so amazing that we have built quantum computers and that anyone can program one and that we can control these qubits and the quantum physics. So I have another question for you, another survey. How many physical quantum bits do you think we have now on one of the largest publicly known quantum computers? Let's see. Okay, interesting. So you guys weren't as optimistic as last time, but the result is actually about 50 to 100 qubits. Okay, it keeps on increasing. Yeah, so as you can see, we've actually made quite a lot of progress, which is really exciting. So that's the hardware. Now, you may have heard recently there's this whole thing in the news called quantum supremacy. This was a few months ago. And exactly what is it if you haven't heard about it? Well, basically, it was a race between the fastest classical computer, so a supercomputer, and a race between the quantum computer. And they gave it a particular problem, and they said, go. And it turns out that the quantum computer could solve this problem in 200 seconds, And the supercomputer would solve this problem in 10,000 years. So they didn't actually wait 10,000 years. They estimated that it could take that long, obviously. So, and as you can see, this was done on a real quantum hardware. And that's why it was a big milestone, and it was in the news, because this was actually the first time it was demonstrated that an actual quantum hardware could outperform the world's best classical hardware. And so, as you can see, this is our current state. We have around 53 qubits. This was done with Google's quantum computer that has 53 qubits. Now, I talked about all of these potential applications of quantum computing at the beginning of this talk. What does that need? Well, really, that needs, so here we've solved one problem faster. So the potential applications really need a quantum computer that has millions of qubits. And this would enable us to solve many useful problems. This ultimate goal would revolutionize the world. It would, because that would break the encryption, that would allow us to design new medicine, new drugs, that would impact finance. We could do a lot of amazing things with millions of qubits that are high quality, I should say. And this is called a large-scale quantum computer. And this is the ultimate goal in quantum computing, to get to this point. But as you can see, there's kind of this gap in between where we have maybe hundreds of qubits and thousands of qubits. And I call this the quantum unknown. Who knows what's going to happen here? So, obviously there's some potential possibilities. One is that for the next few years, even as the hardware improves and we increase in the number of qubits, we don't really solve that many new problems until really we have a larger quantum computer. And this would be okay, but it wouldn't be as exciting because we'd have to wait a bit until we get to that point. But another possibility is that actually now people start figuring out, oh, with this quantum computer with only, let's say, 100 qubits, we could solve this problem. Then we could solve these problems, then these problems, then these problems. And it turns out, even with a quantum computer with only hundreds or thousands of qubits, we could solve many useful problems. And this would be really exciting. And my next point in this talk is that this is actually an opportunity. I think this quantum unknown is an opportunity for developers. Why? Because obviously the hardware just continues to increase. But really, what depends, whether it's that curve or that curve, depends on whether people can come up with new quantum algorithms, whether they can program a quantum computer to do something interesting or useful. So this is why it's a really exciting time, because no one knows if it's possible to get there, but if you could make use of a quantum computer with only 100 qubits or so. And so that's why I think we need to develop the next developers for quantum computing to get excited about this. And the great thing is that anyone has access to the quantum hardware through the cloud. I showed you the Java API, but there's a lot of other, in other programming languages, and you can basically actually run it on a real quantum computer for free for maybe 5 qubits through the cloud. And if you think about it, that's amazing, because when our classical computers were first being built, you had to physically be at the classical computer to program it. But now we have this unique opportunity to just do it from our home. So there's no high barrier to entry to quantum computing anymore, except that you need to learn quantum physics. But other than that, so this is the progress. As you can see, there's a great opportunity, and that's why I'm so excited to work in this field. So overall, this is what we've talked about today. We've talked about the potential of quantum computing, how we can program a quantum computer, and finally the progress that we've made in the field. So what needs to be done in this field? As I mentioned, we need to improve the hardware. There's a lot of big companies that are working on this every day, and people actually think the number of qubits are increasing according to an equivalent of Moore's law. It was just in maybe 2016 that we only had 5 qubits, and now we have 53. So they're continuing to improve, which is really exciting. We also need to find new applications. That's where the developers come in. They need to create quantum algorithms, figure out, is there a way to use a quantum computer with only tens or hundreds of qubits and find some application for it. And then finally, I think we need to shift our mindset from the classical world to the quantum world. As Peter Shor, who created Shor's algorithm, the one that could find the prime factors of a large number, he actually wrote a paper on this, and he said, why aren't that many people coming up with quantum algorithms? And he says, well, computer scientists think classically, right? They've thought classically all their life. So it's hard to shift to the quantum side, but there's a lot of interesting stuff that's being done around, there's like quantum games, there's quantum hackathons that I've been to that are really exciting, and people are really trying to shift our mindset to this quantum realm. So I think there are two future states of the universe. There's one that does not have a large-scale quantum computer. This is the one with millions of qubits. And there's one that does have a large-scale quantum computer. Right now, we're in a superposition of both. Who knows what's going to happen in the future? But paradoxically, our goal as researchers and developers is to break that superposition so that one day we have a quantum future. Thank you.